In the second part, I'm going to introduce this toolbox or software called PRoNTo to you. This is actually, I think, the only one or the very first one provide the GUI graphic user interface that can help you easily perform the MVPA on your FMI dataset. And for the citation, this is the paper that the developer group asked people who use this PRoNTo software for the publication to cite this paper. So this is actually published in 2013 in Neuroinformatics. And the data set that we are going to use today is actually from this, the most earliest one paper right here, the science paper right here. So sometimes we say the data set called Haxby data set because he is the first author right here. Okay, so it's also a very important point that why I picked PRoNTo, because this is the only software or only toolbox also provide these toolbox for you to practice or to learn how to use this kind of environment. So I like this one because in our first part we also introduced this paper. So I think it's a very good starting point for you. Okay, so right now please open your MATLAB and include the PRoNTo. Right now is version 2.1.1. Include the PRoNTo path in your MATLAB path setup. So let me do this. So set path. Okay, so I'm going to include this PRoNTo underline v2.1.1 folders right here. Okay, and save and close. And once you set up the path, now you can key in the PRoNTo, all in the lowercase right now. PRoNTo without n. Okay, PRoNTo right here. Then you will see the welcome message right here. And just wait for a moment. Then you will see the main interface right here. Okay, so basically this toolbox, the full name of this toolbox is actually called Pattern Recognition for Neuroimaging Toolbox right here. So actually it also supports the multi-model data. For example, EEG or MEG data set. You can do so. Okay. So right now the PRoNTo actually provides the possibility that you can use the machine learning approach to do the classification based on the fMRI data or the EEG or MEG data. Okay, just some functional data set. You can perform the classification analysis, but also you can build a regression model that can actually help you to correlate two different things. For example, you can correlate the functional data set with the behavioral data. You can use this kind of a regression model right there. Okay, but today, because of the time, I may only demonstrate how to perform this kind of the classification right here. Okay, so if you want to know the detail, they also provide menu within their toolbox. I think there is a subfolder called menu. You will find a PDF file. Otherwise, I also copy this menu into the folder that I provided to you today. Okay, within this FMI analysis 15 underlying materials, you can also find there is a PRoNTo menu that I just copied from the subfolder provided by this team. Okay, so for this interface, they actually provide a very intuitive way to perform the analysis. You just start from the main steps panel right here. Start from the first panel to specify the data and design. Then go to the prepare feature set. That means to extract the Faxos information or Faxos data value, and then specify the machine learning model right here, and then run the model. And this one may be optional because you can also directly run the model after you specify the model. So this button, sometimes you don't need to click this one. And the final one, you can compute the weights. That means you can explore or to observe which Faxo may provide the most valuable information for the classification. Okay, and for the right-hand side, the review options right here, you can review the data, review the kernel. This is actually a very important thing behind the SVN, or review the cross-validation model, and also display the results and display the weights that are calculated from this button right here. Okay, and you may find out that also this interface also provide the batch process right here. That means if you have multiple data sets, you can also use the batch button right here. And then once you click this button, you will find out they actually use the SPM batch interface. They just use the same core technique, the same core interface right there. Okay. Again, today we only have one data set, so I'm not going to tell you how to use the batch. You can just read their manual and follow the steps. You can easily find out how to do so. But today I'm going to give you a walkthrough introduction about how to do the analysis right here. Okay, let's start from the very first step, data preparation. In this toolbox, they don't provide the function to help you perform the FMI preprocessing. They don't have this kind of function. So you need to use the, for example, SPN to finish all the imaging preprocessing. And I'd like to emphasize that please, for the preprocessing stage, do not apply the spatial smoothing. That is not what we would like to use in MVPA. We'd like to preserve the pattern for each function right there. So we don't need the spatial smoothing. This is a very important thing that you need to keep in mind. Okay, so right now you can go to this hexy underlying data set subfolder right here. Again, this is actually provided by the PRoNTo team. I downloaded it from their website, and then I just included it in our materials data set right here. So you can see there are three different subfolders right here. The very first one, design. You need to provide the imaging parameters right here. So I just crop this one. Oh, sorry, this one. You can see there is a PDF file right here. If you open this, you will see the same values on the slide right here. So they try to tell you what is the imaging parameter, what is a TR, and the design matrix unit is the scan, not second. You can pick second or scan, but normally we use the scan. And the duration for this block design, they actually use a block design to deliver all different kinds of the visual stimuli. They use a block design. So you can see the duration is 9 scans right here. So with TR as the 2.5, you can see the block length is around, I think, 22.5 seconds. Okay. And the onset time, you can see actually they include 8 different categories of the pictures right here. Faces, houses, cats, shoes, and so forth, so on. You can see, and you can see the onset right here. So you can count. Actually, they have 12 different blocks for each category, each picture category right here. Okay, so this is the design you need to know. So if you want to use your own data set, definitely you need to know the onset, no durations, or something else. And you can also find there is another file, spn.met file. This is the file you need to construct using SPN12. Within SPN, we have introduced that you can do the design matrix, or you can specify the first level model. And this is the one function that you can create this kind of SPN.net. So this will store all the necessary information that we will directly input this file into the PRoNTo interface. Then you will know what is the TR, what is the scan, duration, or onset. It's all recorded within this SPN.net file. Again, it is generated by the SPN12. Okay? And for the second subfolder, FMI is actually stored all the preprocessed FMI data right here. And you can see all the file is start with W. That means it's already being normalized. However, without smoothing process right here. So you can just pick one of the imaging, try to take a look on it. So you can see now this is a normalized imaging. So you can see the shape or the geometry is pretty normalized right here. And you can see the imaging size right now. The voxel size is 3 by 3 by 3 right now. Okay. And unfortunately, they didn't provide the normalized anatomical imaging right now. So we only have the normalized functional imaging right here. And you can see they include, I think, 1,452 columns right here. So you have 1,452 time points right there. Okay, and these all from one single subject. So we don't have the second or third subject. We only have one subject right here. Okay. And the final subfolder is masks right here. So this mask actually provide you two different masks. The very first one is the whole brain mask. So you can see this is actually a binary mask to tell you which part should be the brain region that is included for the analysis. And another one, you can see the file name. You can see the file name is fusiform gyrus. That means because the Hexby, the author, already give you a very strong assumption that they want to focus on the fusiform or the FFA region to tell the difference. So you can see this one. This is the fusiform mask. Again, one for the region that they like to include for the subsequent analysis. 0 means they will exclude from the subsequent analysis. Okay, so you can imagine that if you have other kind of the hypothesis, for example, you want to focus on the motor region, then you can create the motor mask from the, for example, AAL atlas. You just pick region 1 and region 2. That means the bilateral precentral region for the primary motor cortex. Okay, so you can create a mask by yourself. However, this is provided by the PRoNTo team. Okay, so you can see the essential files you need. So you need to prepare. If you want to perform the MVPA, you need to prepare these kind of things. And I want to emphasize another point that normally we always say that we need to collect sufficient data set for statistical analysis. For example, normally for the FMI or MRI research, we need to collect at least 30 to 50 subjects within one group. For example, healthy group and a disease group to perform the statistical analysis. However, for MVPA, this is actually designed for single subject analysis. You can do that for single subject only if you have sufficient sample for the stimuli. If you have sufficient sample right here, actually even single one subject, you can perform the analysis. You don't really need to collect 30, 50 subjects to do so. So MVPA, sometimes we say this is a brain decoding, right? When we say brain decoding, that means I don't want to decode a group of a brain. I want to decode a single subject's brain. Or sometimes you may hear the term called BCI, brain-computer interface. That means I want to focus on individual's brain state or individual brain activation or individual brain pattern to perform some kind of a classification to trigger the computer response. Okay, so I want to emphasize MVPA, you don't really need too many subjects to do the analysis. You can focus on single subject. However, the study design, again, you need sufficient sample data right here. You need sufficient runs, sufficient blocks, so you can perform the machine learning. Okay. Okay, now we come to the step 2. Please click the button. I think the click button within the main step panel right here. There's a button called Data and Design right here. Just click this one. Okay, so I'm going to show you how to do so. So from the very first step, you need to assign or specify the output folder. So now what you're going to do is come back to your data folder. You can just create a results folder right here. So again, you can just modify your current folder, so it will make you easier to select the folder. Okay. So right here now, I'm going to pick this results folder as the output folder right here. So now you can see, just make sure there is no Chinese character or the space right there. And then you come to this first list box right here. It will let you assign the groups. So for now, I only have the single subject, and I know that this subject belongs to a healthy group. So I just say, you can key in anything you want. I just say HC, okay? Just a healthy control or healthy group or anything. And for the second list box, now you can input or identify how many subjects you have. So right now, I only have a single subject. So I just use the default value as 1 right here, single subject. So if you have multiple subjects, you just try to add in as many as you want, okay? And the third list box right here is the modalities or the run. So again, we click this add button right here. So modality means you can key in FMI, MI, EEG, or MEG, or something else. Again, the name can be specified by yourself, so you can key in anything you want. But normally, you can just select the enter new I will use the fMRI. Okay, it's just a string, so nothing important. So design right here, they have 3 different options right here. You definitely don't want to pick the no design. So what you can do right here is, first of all, you need to load an SPM.MIT file. This is the one that you need to create it by the SPN 12. Okay, but right now we already have this on hand. This one, SPN under the design folder right here. Just pick this one. Once you pick this one, now you can click this pop-up menu again. But now you can click the specify design. After you load the SPN, you can specify the design right here. Just wait. Now you can see this is the design matrix you load in based on the SPN.MIT file. So you can see we have add different conditions right here. Faces, house, cattle, something. You see the onsets, you see the duration, and you see the unit is scan, and the TR is 2.5 seconds right here. Okay, just try to make sure right here. And then if you want to change anything, for example, the condition name, you just select this one and type anything you want. Again, if you want to modify the onset, you can just change the value right here. Okay, so this is the chance that you can modify the design. Okay, and the final button right here is a select. You need to select all the preprocessed fMRI data, or specifically the normalized fMRI data right here. So select this one. Now you can come to the subfolder fMRI and just select all. So 1,452 files already be selected. Okay, so right now you can click OK right here. So you can see now you have the several different files right here, and then you have these modalities right here. So of course, if you have the multi-modalities data on hand for a single subject, you can again add in another, for example, EEG or MG or something. Okay, and then come to this mask button right here. In this situation, I will pick. You can select this fMRI, and I will pick the file under this masks subfolder right here. I will pick this whole brand.img right here. So I just get rid of all the background voxels. I just want to focus on the brand voxels right here. Okay, so you can see the red color becomes black colors right here. And then before you click the save, you need to click this review button right here. So now in this review figure, you can see, first of all, how many subjects do you have? So we have one group HC, and we have only single subject. So if you specify several different groups, you will see different bars right here. And now this is the number of the selected scans right here. So you can see actually for 8, you can see different color bar means different conditions right here. We have several different scans right here. Okay. And the final one is the number of the discarded scans. When we will discard this kind of a scan, it depends on this. Depends on the design of the hemodynamic response function right here. You can see originally we don't assume there is any HRF effect. However, as we mentioned before, that based on the neurovascular coupling, our vessel may take several seconds to respond to this kind of the neuronal activity. So actually we have some kind of a delay right there. And the delay, definition of delay in PRoNTo is actually the time it takes for the hemodynamic response to peak value right here. So normally, as we introduced before, this value should be around 5 or 6 seconds, right? And then you can also key in another parameters right here we called HRF overlap. Again, this is defined by PRoNTo, and actually this overlap means the dispersion or the width of this HRF function right here. So the typical value right here is 6 for delay, 6 seconds for delay, and 6 seconds for overlap. Just both are around 6 seconds right here. So what you should do is to key in these two values right there. Then the MVPA can help you to shift the border signal or shift the anticipated response right there. And sometimes you may see, let me try for you. When I put 6 and 6 right here, you will see it seems that there's nothing happen, right? But if you increase this overlap correction to a larger value, for example, 20 seconds, you will find out that actually the discarded scans become larger and the selected or available scans become lower. Because when you consider large width of the href function, that means you may introduce the overlap between two different consecutive conditions right there. In this case, what PRoNTo does is they will directly remove the overlapped blocks or overlapped scans right there. They won't simply correct anything, just discard them. So this is the parameter that you can set up. But normally we just set up 6 seconds right here. So if your study design didn't give too short resting interval, normally you will not see any discarded scans right there. That means all the scans can be available scans right here. Okay. So once you finish it up, just close the window, and now you can go back to the setup window right here. I may remind you that when you perform the PRoNTo analysis, I may recommend you that just put the manage command window under this user interface, because the command window will keep updating some kind of information or message to you. So you can see once you close the review window, it will again tell you the design in PRT.met update. What is the PRT.met? They actually try to mimic what SPN did. SPN will create so-called SPN.met file. So PRoNTo will create a so-called PRT.met file for their own specification. Okay. So what you're going to do right now is you need click the save button. If you didn't do so, you won't see this kind of message. That means what you did just in fact, you will just you won't have any setup in your file or in your model. Okay. So right now you can go to the results subfolder right here. You can see there is a PRT.met file. We will use this one to go for the next step. So this is very important. So every single time when you change anything, for example, you change the file and you change the setup for the href, remember to click the save button again. Okay, this is very important. So you can see only if all the texts on this interface become black, all in black text, that means you finish all the steps. If you see there is something in red text, that means you need to do something. Okay, so this is kind of the reminder. So once you click the save, and then you definitely see the this kind of the save down message on the command window, you can quit this this interface. And now we come to the second button, prepare feature set right here. Okay, so right here again, I actually leave the parameters on the slide, but now I'm going to just display how to do so for you. So again, I leave the command window behind this window. So very first things, you need to select PRT.met file. So I click this one, and it will automatically point to the output folder for you. So just click this PRT.met file. Okay, and then once you select the PRT.met file, there's a new window pop up. And what you're going to do is you need to select the modality, but since we only have one modality named as the FMI right now, you just select FMI. And the conditions right now, we don't want to treat all scans right here. We want to treat all conditions. We do have the 8 different categories, right? So we pick the all condition. We have 8 conditions right here. And the parameters right here, there's a detrain. Detrain is the way that we can correct the signal drifting. And for FMI dataset, this is very, very important. So if you are using the FMI, do perform the detrain. And I may recommend you use this polynomial. And you can just preserve the order by 1. That is a linear detrain. Okay, linear detrain. This would be enough. And this scaling option right here is actually designed for the quantitative measurement. For example, if you have the paid data on hand and you calculate the SUV, and then you can try to scaling this value by specify from some net file or something. However, for FMI, this is not that important. So you just keep no scaling right here. Okay. So for the feature extraction right here, you will have 2 different buttons right here. You can either specify so-called second level mask. That means I'm going to apply a further mask on our feature extraction. If you may recall that we actually select the whole brand mask as what we did in the data specification, right? But right here, we can further select another mask. For example, we can pick the Fusiphone gyrus mask right here. So this is a mask that we can actually confine or control our feature extraction only from this Fusiphone gyrus. So we use the whole brand mask as the first masking to get rid of the background voxels. But then right here, we further use the Fusiphone gyrus mask to extract only the voxel from this Fusiphone or FFA area right here. And you can see there is another option right here, is that you can actually use the atlas-based ROI. So what you can do right here, you can actually click this checkbox and select the AL atlas. And we see in PRoNTo subfolder, they actually provide an atlas subfolder, and there is an AL atlas, 116 AL atlas imaging inside. So you can pick that. But for now, because we have a very strong hypothesis that I'm going to test whether FFA may be a critical region for us to classify the brain states when looking at the human face or other things. Okay, so let me click down right here. And now you need to give a name to your feature set. So right now I just want to say maybe FFA feature set. Feature set. Okay, so I just key in short, FFA, Fusiphone, or face area, and feature set FS. Okay, this is anything you want, just key in. Okay, and now I only have the one modality. If you have multiple modality, you can concatenate them. But right now I only have one. Okay, right now you can click build kernel and data matrix. Again, then you will see some processing message just keep printing out in your MATLAB command window right there. It won't take too long. I think within 1 minute it will be done. Okay, so once you see the processing done messaging from the command window, then you can proceed to the next step. We call step 3 specify model, machine learning model. Okay, so what I'm going to do right now is I'd like to check. Okay, it's only for 6 blocks. Just wait. Once it's finished all the blocks, then it will be done. Okay, so now you see saving message and the down message right here. So now you can see when you go to the result folder right here, now not only the PRT.mat file, you can also see there is a feature set file right here called FFA_fs.mat file right here. Okay, so this is a feature set data. So once the feature preparation is done, you can see the prepare feature set window will automatically close by the PRoNTo. And now you can proceed to the next step, next button, specify model right here. So click this one. Okay, so again, always start from assign the PRT.mat file right here. So again, we select the PRT.mat file. Click down right here. And now you can create several different models using different machine learning, different cross-validation method, or something else. So right now, again, you need to specify a model name. So to me, I just want to key in test model or something. You can key in test model 1, 2, 3 if you have several different models. Okay. And the feature set right now, you can see actually we can create several different features from the previous step. But we only create only one, right? So if you have multiple different feature sets, for example, you'd like to test Fusiphone, you want to test the parahippocampal region, you can create different feature set in the previous step, okay? But because of time, I only created one for you right here. Okay, so now we come to the model type. You can see that you can select the classification or regression, okay? But right now, we only display how to do the classification. If you want to know how to perform regression analysis, go read the PRoNTo menu. Okay, so we select the classification, and now we can define classes right here. And the define classes interface right here you can first of all determine how many classes you'd like to classify. So to me, I'd like to keep things simple. Right now, I just keep 2. I just key in 2 right here. So I want to differentiate 2 different classes. Of course, in this data set, you have 8 different conditions, right? So you can actually create 8 different classes. However, more classes, I can tell you that the accuracy will become lower and the things will get pretty massive. Okay. So right now, I just key in 2. Once you key in 2 and press the enter, then you will see this pop-up menu will give you 2 different options right here, class 1 and class 2. Okay. Now you need to select one of them. For example, I select the class 1 in the very beginning. Once you click the class 1, you will find that the disabled list box will become enabled right now. So you can select which group do you want to select. So which subject do you want to select? So right now, I will pick the first subject or the only subject that we have. And for the very first class, I'd like to take the phases condition as the samples. So you can change the class name right here or not. It depends on you. So I'd like to change to phases right here. And again, I'd like to tell you that actually you can include several different conditions within one class. Remember that. For example, if now I come to the class 2 right here, you can see you can again select the subject. You can actually select the houses, cats, shoes, bottles as a class 2. So I can say this is actually the objects right here. So you can actually combine different conditions within one class. But again, normally we don't do so because since we add different categories, that means normally we think that behind these add different categories, they may have different response right there. So I won't really pick so much. I just want to tell you that you can do so. Okay. So right now I may pick the houses, just houses right here. So with a pretty similar idea, you will find out that actually you can pick several subjects. So if you have 5 different subjects, you can combine subjects as one group. It's okay. Okay. Okay, so right now, once you specify the houses, now you can click done right here. Okay. If you didn't specify all the necessary items, you will see when you click done, nothing will happen. And you will see message from the command window saying you need to specify everything. Okay, and now you can go to the machine or the model selection right now. You can see for the PRoNTo, they only provide 3 different model right here: binary support vector machine, binary Gaussian process classification, and multi-classed Gaussian process classification right here. I can tell you that for 2 classes classification, you can use all of them. However, for multi-class, that means more than 2. For example, 3 classes, 5 classes, maybe only the multi-classes GPC can be used because the very first 2 are only used for binary classification. Okay, so just pick anyone. So right now we just pick the support vector machine. And actually you can optimize the hyperparameter. This based on whether you know SVM or not, but they have some soft margin parameters that you can optimize using some cross-validation scheme during the training period. So right here, you can click on this one, and you can pick what kind of the cross-validation scheme you'd like to use. To me, I always use k-folds because to now people tend to believe that leaf-one-out may cause some overfitting or some not reliable results. So right now I always use the k-folds cross-validation right here. So you can specify how many folds you'd like to use. Right now we key in 5. Okay, we don't have too many samples right here, so just don't put too large numbers right here. I just put 5. Sometimes 10 would be better, but right now I key in 5. Okay, so this is a stage that how you specify your model. And the final one is the cross-validation. This is very important when you try to measure or try to determine the performance of the model right here. So again, for the cross-validation or for the testing period right here, you still need to specify one of the cross-validation approach. So right now, I will again pick the k-folds CV on block. Okay, I'll use the 5-fold cross-validation right here. Okay, and the final list box right here, you can see you will have the chance to do the data operation. For example, you want to adjust the mean value, normalize the value for the feature set. This is the common things that we should do. Okay, and at a minimum, I think the third step, mean center features using training data, is very important. You need to at least do so. But for now, based on this data set, after my try and error, I would say you need to include the first one, third one, and this one. So I may include a sample averaging within block, and mean central features using training data, and normalize the samples right here. This is the 3 steps that I'm going to use before I'd like to send up my features to the machine learning model right there. Okay, so this is all the things you need to do. Once you learn the machine learning in details, you will find out actually they didn't provide too many options to you. But however, I think for MVPA analysis in FMI field, I think this is good enough. Okay, just after you specify all the items, click this button, specify, and run model right here. Just don't worry about that. That's just a warning message that because for the hyperparameter optimization, I didn't specify any predefined values. So it just tells you that they will use the default value to do the optimization right there. Okay, so you can see after a quick calculation, there is a done message right here. So now it's a good timing for us to review the result. So now we can jump to the right hand side. You can see there is a display results button right here. Again, we don't need to click the run model button right here because we already clicked the specify and the run model button. Okay, so right now we click this display results right here. Once you click the display result, it will again ask you to assign a PRT.mat file right here. Okay, so in this interface, you can see so many different information right here. So you can click on one of the fold right here. As you may recall, we use 5-fold. That means we will separate our data set into 5 different combinations. We use first of the fifth portion to be the test data set right there. Okay, but for now, we can just use all folds or average result to see the result. Okay, you can see we can start from the histogram right here. You just click fold on all folds and average, then click on the histogram right here. Again, if you have several different machine learning models, you can click on them, but however, right now we only have one. Now you can see we have, based on the histogram, actually the mean difference is pretty obvious, and we may have a very strong evidence to find a good cutoff point right here. Okay, and then you come to the confusion matrix right here. Confusion matrix is a very useful one to tell you how the true classes can be predicted in the correct way. If you have the true class belong to the first one, that is the fast. And you can see the predicted value weighted the machine can also classify this as a first class. So you definitely want this value and this value to be as high as possible. That means machine predicted by machine always make the right decision. However, you still can see there is a wrong decision right here. 2 of the second class become the first class. That is a misclassification right there. However, this result is good enough. You can see that statistics right here. The classification accuracy for the balanced one, that means the overall accuracy is around 91.67% right here. And the class, that means when we look into detail, class 1 and class 2, you can see class 1 has the 100% accuracy, and class 2 has around 83% accuracy. That means based on this fusiform area, you can actually use the voxel to tell whether the subject is looking at the face pictures or looking at the building or houses pictures right there. And now you can click on this option, predictions right here. Now you can see this is actually after the SVM conversion. You can see this is the support factors value right here. You can see normally after the SVM model, we will have the negative value represented for one group and the positive value for another group. So normally we will set 0 as the threshold or the cutoff point. So I would say any data set come into this model when they have the converted value with a negative value, then I will say this is belong to this class. That means the houses class, and this one is the faces class. So you can tell that these 2 samples actually will be misclassified as the faces right here because they have the positive values right here. So this is the reason why houses didn't have the 100% accuracy. Two of the sample actually misclassified as the faces right here. And another important thing is the ROC, receiver operating characteristics curve right here. I should enlarge the window. Okay, for the vertical axis right here, they represent the true positive. And for the, I didn't see this one. Maybe I have on the slide. Okay, for the horizontal axis right here, this is the false positive one. So what we'd like to see is actually we want to have the as high as possible the true positive rate is, and we have as low as possible the negative positive value is. So we want the curve actually located in this part. We have 100% true positive and 0% false positive. That would be the best case right there. But you can see right now the ROC curve, the area under ROC curve is around 0.96 right here. So this is pretty good because the best case is the area of 1. And now the area is 0.96. So this is a very good performance right here. The final option right here is the hyperparameters. If you may recall, we try to let the machine to optimize its hyperparameter, right? So you can see the best parameter is located in this one. And they have the high frequency of the selection and the highest balance accuracy right here. So this parameters is actually optimized for this model. The final thing I would recommend you to perform the permutation test on this accuracy result, because normally we can claim that the accuracy is 91 or 100%, but how strong confidence or evidence do you have? You need to perform some kind of a statistical analysis. However, in this case, what we can do, we don't have multiple subjects. We don't have more samples. So what we can do right now is to use the permutation test. We will do the repeated sampling to confirm this p-value. So normally you need to set up the repetitions to around hundreds to thousands. But because of time, maybe I just try 100 right here. Okay. So you can see currently the p-value for balance accuracy and the class accuracy is not available right now. But after you calculate the permutation test, you will see the p-value right here. So I just set up 100. You can try more, but it takes more time for sure. So let's go to this one. Now you can see Commando now telling you that they are doing repeated sampling right now. So we need to do this for 100 times. So just wait a moment. Let me put this right here. So once the all the permutation is done, you will see the p-value display right here. So you can see now we have pretty strong evidence to say that p-value is pretty small, around 0.0099. Okay. So for my recommendation is that every single time when you try to report this kind of accuracy value, you can provide with p-value. Okay, of course using a permutation test, so you can better convince others that this kind of the accuracy is reliable. Okay. So this is actually the general walkthrough that how we perform the MVPA based on a small area focused on the fusiform gyrus. However, there is one more step that you can do. This is optional one, but normally this is a very useful one. That you can click one more button right here. There is a compute weights button right here. If you want to know which voxels within the fusiform gyrus actually provide more information or give a high contribution to this kind of the classification, you can try to calculate or compute this kind of the weights. So click on this compute weights window. Again, you need to select the PRT. Then you need to select the model. So since we only have the only one, I just click this test model. And there is a chance that you can modify the weights imaging. But right now I just keep the default value right here. Okay. And if you actually want to know so-called atlas-based weights, you can select the atlas. However, we only focused on the fusiform, right? We didn't perform the whole brain analysis. So for now, I don't want to click this one. However, if you use the AAL Atlas as the feature extraction step, you can click AAL Atlas again as the Atlas best weights. So they will calculate a single weight value for each Atlas region. Okay, but for now, we don't pick this one because we only want to focus on the fusiform. Click compute weights, it will be very, very quick right here. Okay, then final step, click display weights right here. Again, you need to specify the prt.mat file right here. Then you will come to this display window. You need to select which model you want to display, this one. And you have only one weights model right here. So now you can see this is actually, you can see this is the shape of the fusiform right here. Now you can tell, okay, which part may have the higher weights right here. So you can see, okay, when I try to classify human face from the building or the houses, you can actually say fusiform may provide very informative features to do the classification. As we can see, the accuracy is pretty high, but also I can tell you that actually a certain portion of the fusiform may contribute more compared to other voxels within the fusiform. Of course, right here you can try to move your crosshair, and you can see there is an updated MNI coordinates and the voxel informations right here. And also, if you have the anatomical imaging you want to put as the underlying imaging right here, you can read one. However, I say unfortunately this dataset didn't provide the normalized anatomical imaging right here. So if you have one, I would recommend you to put this on here, under this kind of the weights map right here. So now you can claim in which brand location, specific location, what kind of the weights map that can help you determine which portion of the fusiform may contribute more to this kind of the classification right here. Okay, so to this point, I finished all the steps. I just try to give you a general idea. It's a very useful one, at least the one that can help you learn the general idea that what you can get, what is the result, what is the map that you can have. So think about this. If you want to know more, you need to try another data set. As I introduced before, PRoNTo also provided 3 other different data sets. So you can download others, or maybe you can try other different conditions. I only use the fast and the house. You can try other conditions to see whether you can get a good or responsible result. So if you have any question, just come to me.